So this is just the front cover of Geophysical Research Letters that was published in the July edition in 2001. And that really summarizes the results of the South African seismic experiment. And that was something that, in fact, Sue knows a whole lot more than me about, or because she was involved with it. I wasn't at WITS at the time, and I wasn't directly involved with it. But I worked with students and other people working on the data afterwards. But that really was a deployment of seismic stations, 83 of them, all the way from the Cape Fold Belt from Cape Town into Zimbabwe. And the intention was to look at the structure of the crust and upper mantle. And this summarizes the main results. So firstly, if you look at the top, that's the topography. And you'll see there the various major tectonic domains over there, the Carpal Craton, the Namakwa-Natal Belt, the Cape Fold Belt, the Popa Belt, the Zimbabwe Craton. And what we really notice over here is the elevated topography, which is one of the things that we are trying to understand. Then down below, you see the map of the MOHO that was determined by receiver functions. And you can also see there it's shown in different colors over here. So you can see where it's shallower and where it's deeper. And then down below, you see the mantle lithosphere over here, the roots of the cratons extending down to depths of perhaps 250 or 300 kilometers. The colors over there, the blue colors, that's where the velocities are higher than the standard mantle model, and the red color is where they are lower than the standard mantle model. These colors, of course, are used because all other things being equal, the chemistry being the same, you would expect faster velocities in cold rocks, hence the blue, than in warm rocks. Right, let me skip over that. Just to show, and this one I had here because I hoped Lebo Odisha would be here, and this is just to show some work that I did prior to the Carpal Craton experiment. Where
Ray, just to say, Lebo has just joined.
Okay, thank you. So these were seismographs that were set out on profiles between Klerksdorp and Witbank, and also from Boksburg and Welkom, where we left them out and would leave them recording in the field for several weeks until we had enough data at each site. And this also should make the people who are now using these electronic systems realize how easy they've got it. In those days, we'd record on these big tape decks over here, a lot of equipment to lug into the field, and those tapes would often jam. But in the end, we recorded the full waveforms, and we were able to construct record sections, as you see below. And from that, we were able to interpret, just using refraction seismics, but not only using the layered earth model, which would allow us to pick up the depths to MOHO, but also using our wide angle reflection. If you look at the distances between perhaps 120 and 170 kilometers, you'll see that there's a very strong amplitudes coming through at a reduced travel time of perhaps 18 to 20 seconds, and that is the wide angle reflection. Of course, you can also see reflections from mid-crustal discontinuities as well. And that's part of what Lebo will be looking at using the Bushveld data, is to do this kind of analysis. But let's carry on. What we came up with there at that stage, of course, was a model of the crust in the Archean area, the Proterozoic crust as well. And we interpreted it in a paper that we published in the mid-1990s with Walter Mooney over here in terms of the evolution of the lithosphere in the Archean and the Proterozoic times. And so we didn't just stick with the seismics. We said, well, let's try to learn something about geochemistry and not leave it to the geochemists to, I suppose you could say, lick the cream on our models over here, but we had a go at it. And this paper was published in GR, and it still continues to get quite a lot of hits and citations. But I suppose the main thing that we came up with, that if you see in the top left-hand corner, you can see a model there of, and that was published in the textbooks at the time on crustal structure. And generally the belief was that the older the crust, the thicker it would be. And they took, and they fitted this line over here going from oceanic crust through Phanerozoic, Proterozoic, and even to the moon where the crusts are very old. And they said, well, look, the older it is, the more it's had time to grow. And so our data, we did then also not only stuck with the Southern African data, but we did look at a worldwide synthesis of crustal structure, seismic models of structure as a function of time. And we found that, in fact, the Archean crust didn't fit that trend. And that was part of what we tried to explain. Of course, since then, I mean, the last 25 years, a lot more experiments have been done. And it's like everything in life, it turns out to be not quite so simple. But anyway, it's always good to put out a bold model, because then people try to disprove it. and you can get some citations saying, unlike Durrheim and Mooney, we found. And so it's a good way of doing things as well, trying to test some bold hypotheses. Also, what is, I suppose people tend to forget, back in 1997, just prior to the South African seismic experiment, there was a international symposium on plumes, plates, and mineralization over here, held in South Africa at the University of Pretoria. And as part of that, we held a workshop over here, which we called the Geophysical Framework of the Copland Craton. And Sue and I hosted that session. And the whole idea was to try to identify you could say, the key unsolved questions that we hope that the South African seismic experiment would cast some light on. And so that was quite fun to pull that together. So of course, these were the days when in Saga we were attempting to launch our own journal, which didn't quite pan out because we just, I suppose, don't have enough papers being produced in our community to sustain something like this. And it's also a bit of a chicken and egg situation for us as academics to get credit for your publications. It needs to be in an accredited journal to earn the subsidy. And for a journal to become accredited, it has to publish consistently for several years. And so it's a kind of a chicken and egg situation, and we couldn't get that launched. And that's why we had 3 editions of this Geophysical Review. And since subsequently Saga decided to support the South African Journal of Geology, and that's where we sometimes have special issues and special sections. I went mining for a while, but this is just now to get into looking at what can be done with the South African seismic experiment. That's just looking at the distribution of the stations, again from the Cape into Zimbabwe, and there were several deployments. The spine was there for the full 2 years, and those on the flanks were just deployed from, were set out in 1 year and then moved to the other side for the next year. You'll see, of course, when you're dealing with receiver functions and surface waves, the more earthquakes you can record, the better you can improve your signal to noise ratio by stacking them. This is just a picture of those seismic stations, how they were deployed at that time. Of course, we do things a bit differently now, but much the same over there. Solar panels, hole in the ground, and cover it up. On the left-hand side, you'll see antennae being put up because there's a section of the array. The main array was 83 stations, but there were another about 30 stations put in a lot denser array around Kimberley, and that was a telemetered array, so the data was transmitted to a central point in near real time, while the other stations, people had to go and visit the sites and download the data. So what did you find? Well, we know when we're doing seismics, we've got a whole tool block box of different methods that we can use in order to analyze the data. So you can take the same set of seismograms and analyze them many times over, looking at surface waves, body waves, and doing joint inversions, and of course combining it with other geophysical and geological data sets. One of the key questions, of course, is what is the cause of this elevated topography here? This is a paper that was published in Nature over here, and this feature over here in southern and central and East Africa is known as the African superswell. What is causing this topography, this elevation of the continent? And of course, what we learn from, I suppose you could say, studies of dating of the topography, that this is a relatively recent topography. Southern Africa used to be at sea level, pretty near sea level, the surface, much like Australia or the US, eastern US, but something caused it to bob up somewhere between 5 and 30 million years ago. So we see the escarpment over here is the erosional feature, and we can see our rivers like the Orange and the Tugela cutting back into the central plateau. Okay, some work on, I'm going to just work my way down from top to bottom, crust and moho. Look at receiver functions over here, and we come up, and there you can see the map of the moho. This was produced by Teresa Nguri, and she graduated with a PhD in about 2001. And these are the stations and the map of moho. Concept is very simple. I think everybody knows that. You have a body wave coming from distance of between thousands of kilometers away. They reach a velocity discontinuity. You get a conversion of your P wave to an S wave. And so you use the delayed wave, the delayed S compared to the wave, one that stays a S wave all the way through, and all the various reverberations over here to come up with a model of the velocity ratio between the P wave and S wave velocity and the thickness of the crust. And so these are the typical data that you get over here. So you can see on the left, you find they're aligned against your direct wave arrival, the P wave that comes through. And then you can see that strong arrival over here. This has been converted from, as you could say, time to depth. And you see an arrival coming in, indicating a depth of somewhere between 30 and 40 seconds. That would be a delay of perhaps 4 or 5 seconds over here, your S wave compared to your P wave. And you can see these are being grouped into our different terrains based on the seismic station, Zimbabwe Craton, Karpov Craton. So there's codes there, SA78, SA80, of course, the station numbers. And the other number closer to the receiver function are the number of traces that have been stacked together to give you this receiver function over here. And so you can see quite a difference between the different regions over here. Generally, like in the Zimbabwe Craton, you've got a beautifully clear receiver function over there. That means you've got quite a sharp boundary. It's consistent over here. While in other places like the Limpopo zone and the Bushveld complex, you can see the conversion is a bit deeper. It's a lot messier. So that means there's perhaps more variation and not such a sharp discontinuity over here. So this is the kind of work that was done back then and will continue to be done using more sophisticated methods like HK stacking. Of course, here I'm just zooming in on the Kimberley array. You can see there's the window on the bottom right-hand side showing those 35 odd stations. Why was it focused here? Well, firstly, Kimberley's where we've got these samples of the mantle lithosphere from the kimberlite pipes, which bring up the xenoliths from deep down below, so we can relate our seismic velocities to actual rock types. And also it's an area where we get a lot of arrivals, not only from distant events, but from our mine, our mining-induced seismicity. And that allows us, of course, when you're using your shorter this travel time paths, you can do different things with it. But one thing over here, what you're looking at are these high resolution receiver function stacks. So in fact, over here, you're able to look at the details of that receiver function. You're able to sort things out, like what is the density contrast that you see across a moho. You do that by looking at the amplitude ratios of your different reverberations. So you can look at things such as density contrast or the thickness of your mantle crust transition, the nature of your moho. Is it 0.5 kilometer thick? Is it 1 kilometer thick or 2 kilometers thick? So we're really trying to pull out as much detail as we can. Also, using mining tremors, it's possible to look at the details of your crustal reverberation, your moho reflections. You can see in that record section there, you see phases marked PMP. That means a reflection, a wide angle reflection from the moho. If you look on the right-hand side, over here, you can see the various traces mapped out and with the different phases picked over there. Your PN is your refraction that travels in the uppermost mantle. Then you get your PMP phase, and then you get the multiple of that. And then you get the conversions of your reflection. How do you sort that out? Well, what helps over there is if you've got your 3-component recording, you can, of course, rotate it. So you're looking towards your source, and then you can see what your polarization is. And from that, you can look at you could say your emergent angle of your seismic wave, and that can allow you to distinguish with confidence between these different forms. So if you compare, this is what we call the hodogram. That's the one just above the ray paths over there. If you look at the PN hodogram, you can see the angle of polarization is different to the PMP angle of polarization. And that you can, of course, explain in terms of your emergent angle. Emergent angle is steeper for your PN wave as compared to your wide angled reflection. So there's a lot of rich information that can be extracted from these waveforms. Right, and in the end, this is the kind of model that was derived for that area of the Karpov Craton. And so it was possible taking xenolith data and our seismic data and these detailed interpretations of the nature of the moho receiver function and reflection over here. In fact, give a crustal thickness to, you could say, even a decimal point of a kilometer, and look at things such as the contrast in shear wave velocity and in density at that transition. So that allows you to do some quite nice interpretation. And we're hoping to do something similar. Let's see to what extent we can do in the Bushveld complex. Okay, other types of work that's done over here, just using standard record sections over here, where you use more distant earthquakes over here, and you plot you just a travel time versus distance graphs. And this, of course, coming from many different azimuths, so it's going through many different types of crust and mantle, and so it's quite scattered. But this is used to derive pretty much standard 1D velocity models over here. So, of course, we can do something like this, but it's just very generic over here. But again, it's you're able to look at differences in different azimuths, grouping together perhaps your P arrivals coming from the north and comparing them from the south, and from the same with S arrivals, getting some sort of regional model over here. This is work that Cedric Wright and some of the students at that time, Rapaleng Simon, Albert Kangaswani, worked on over here. Come up again, interpreted in this in terms of cratonic roots, rock types as well. Let's move on a little bit deeper into the uppermost mantle here. And now, in order to see deeper down, of course, you need sources from greater distances. Much the same figure over here, only previously we were looking at regional distances out to perhaps 800 or 900 kilometers. And now we go into distances, earthquakes, perhaps up to 2,000 or 3,000 kilometers away. And so you see deeper into the mantle over here and can come up with increasingly sophisticated models over here, going deeper and deeper down, looking at depths of perhaps 320 kilometers. Okay, very importantly over here, you see on this P-wave velocity model, you see those black dots over there, and those are the velocities determined from mantle xenoliths over here. So it's very useful to have real rocks over here where you can measure the velocities and use that to calibrate your models as well. Okay, now we move on to another technique. We're using body wave tomography, not just the travel times, but travel times from many different distances, and dividing the Earth down below your array into a whole lot of volume elements. And of course, what you do is you use numerous earthquakes coming from various azimuths. And you're looking at the arrival times of their different phases. And you can see don't just use the first arrival times, you can use reflections, say, from the core mantle boundary in order to come up with a velocity model. You're comparing it always to a standard Earth model over here. And so what you can see over here is just showing just selections of the seismic waves, some coming from the Sandwich Islands event, that's the subduction zone of the tip of South America. And so you see using both the direct P and S wave arrivals and also the core mantle boundary reflections. And of course, they're traveling through different volume elements in the Earth beneath the craton. And then, of course, these are these famous sections that were developed at that time, used to look at the nature of the cratonic roots underneath South Africa. So you can see on the left-hand side are your P-wave models, on the right-hand side are your S-wave models, and here I've just chosen two slices at 150 and 300 kilometers, and then the sections going along the axis of the array over here. So again, you can see under the Carpwell craton, you can see the blue color extends quite deep down under both the Carpwell and the Zimbabwe craton. And the Bushveld complex, of course, is quite different. And that is for this, in this group, we're going to be looking at, I suppose, really zooming in on that area and seeing what we can tell in greater detail about the Bushveld province. So that's just an enlargement of that picture. Then we just go on to using surface waves. You can do much the same thing. Okay, now you find that, of course, surface waves are sensitive to different types of boundaries. One thing is surface waves gives you the actual velocity, not just the relative velocities compared to standard model, and perhaps tends to be more sensitive to vertical boundaries, while P-wave is more sensitive to lateral boundaries. But you can come up with different models over here. A lot of work has been done over the years. And again, you can see these different slices. This is now starting on an African scale over here, looking at differences between the cratons over here, and the top picture is the cratons in Southern Africa, and the whole spreading center of the East African rift system in East Africa, Northeast Africa, and down below here you look at the one showing both the West African craton. And again, you use distant earthquakes, you put them all together, and these are studies looking at in Southern Africa, One of the big questions, unsolved questions there is, the question was, is there a low velocity zone underneath the Karpal craton? And so different people use different surface wave models and different studies, and they came up actually with different answers. It wasn't absolutely convincing over there. Some people did find evidence for a low velocity zone and others did not. So there were a whole lot of studies there. And of course, the students working on this will have to review these papers and see what they can put it all together. So for example, here's the paper from Priestley over here, and you can see the shear wave velocity model on the right-hand side over here, the change in shear wave velocity with depth, and they did not find evidence for a significant, or visible low velocity zone over there. Another something that you'll see appearing on the slide is the word anisotropy, and of course this is something that Benita is studying in a great deal of detail over here, was to see what evidence is there for anisotropy in Southern Africa and what controls it. Is the anisotropy that we see due to current day plate motions? Is it mostly in the, I suppose you could say, in the plastic upper mantle where so it's driven by the convection currents, or is it something fossil that was frozen in from when the mantle lithosphere consolidated? Right, so over here you can see some other studies. This over here where you can see in the shear wave velocity profile on the left-hand graph over there, you can see something of a shear wave low velocity zone at the bottom of the mantle. So this is something that's still depending exactly on how you analyze the data. It's something that we look at. On the right-hand side over there, you can see the geotherm. Okay, now this is very important to understand, bring in other geophysical information over here. And one of the issues over here, we know we get many of our kimberlites in South Africa do have diamonds and others don't, okay? And what is the reason for it? And generally, the idea is that those that don't, what has happened there is the carbon that they would have had in the source regions of the kimberlites would have been heated to a point above the graphite diamond transition zone there, and so they've been turned from something precious into something, from something you wear on the ring to something you put in a pencil. Okay, over here, so something valuable to something just not worth quite as much. So this is an important issue that we also are looking at over here and have to bring into our models, is the issue of temperature, because that allows us also to interpret our size and velocity. Now over here, in more recent years, some people have used, as you could say, display and processing techniques from reflection seismics to make a lot more sense out of your receiver function. So over here, you see all the different stations from the SARC array, and scattered around here, you can see a whole lot of red crosses. And each one of those red crosses is what we call a piercing point. Okay, that means if you have for one station, you'll be recording earthquakes from many different azimuths. And each one, as it comes through, let's say we happen to be looking at the MOHO transition, the MOHO receiver function, depending on whether the wave comes from the northeast or the southwest, it will have a different piercing point. And the idea is now to sort these out and actually get a far better coverage of our, let's say, that transition surface by taking this into account. And one can do that for any boundary, could be the mid mantle transition zones that create these conversions over here. And then this is plotted over here. You can then take, you could say, sections along any arbitrary line over here. And what you plot in over here is the strength of the conversion over here. And what you can see over there, let's say starting from the top, you can see the conversions arriving from the MOHO. That's where it's got a nice red color over here. Of course, you can get conversions that have the opposite polarity depending on the contrast in your velocities over here. So you can see different features appearing in here as you look at this, both your MOHO reflections, and as you go deeper down, you're starting to see conversions from your transition zone and your at the 410 and 660 kilometer discontinuity. Now, some of the work that has been done using this kind of technique in East Africa, Andy Nyblade and Gabriel Mulibo and others, have then been mapping the thickness of this mantle transition zone. Sometimes it gets thinner and sometimes it gets thicker, and that you can relate to your temperature in your mid-mantle over here. That's something that we haven't looked at in detail in Southern Africa on this data yet, and this is something that perhaps we could look at in the future. Again, this is just much the same data, other people working on this data, and here mapping as we go deeper into our upper mantle discontinuities, mapping over here the 410 and 660 discontinuities and variations in this layer. Right, so this is just going even deeper into the world, and one of the exciting things over here is, let's go over here, is again somebody called Stankovic did further work over there using similar techniques. Not time to go into all that. And here we go even deeper over here to look deeper into the mantle. Over here, that you can see the big stars over there are more distant earthquakes over here. And so now we're looking at distances from source to receiver of several thousand kilometers. The other symbols that you see between the stars and the array are the turning points of these seismic waves, the deepest points in the mantle that they sampled. And so you must be very aware when you come up with your models of mantle velocity, they're not beneath the array, but they're representative of the region between your source, your distant earthquakes, and your array. And so now you can see over here, we're looking at distances over here up to 34 degrees, maybe 3,500 kilometers away. And we're probing even deeper into the mantle with these velocities here, seen down to depths of maybe 800 kilometers all the way through the transition zone. I won't go into this in detail, but it's mapping and modeling all the different arrival times over here. You can see over here, this is the S shear wave velocity model on the right-hand side. And you can see there are some models over there that do show quite a sharp low velocity zone in your shear wave velocity underneath your mantle lithosphere. Others don't. So that's part of the question. Okay, and here's now interpreting this data, interpreting the structure of the Earth all the way down to depths of 800 kilometers. Now, I suppose tying up with the whole seismic, well, the whole investigation of the Bushveld complex, we tried to look at, what effect did the intrusion of these large igneous provinces, and we in this unusual situation in Southern Africa that we've had several of them here. We had the Bushveld event. Well, we first had the Ventersdorp lava event. After that, we had the Bushveld event. And a whole lot more recently, we had the Karoo event. And these have all been kind of superimposed on each other. What kind of impression do they make on the mantle and lower crust? And so that's why it's important not just to look under, you could say, the present position of the Bushveld. We must appreciate that it once was perhaps a lot more laterally extensive, but has been eroded away. But also we have to look far enough away so we can compare what the crust and upper mantle looks like under the Bushveld with the regions that weren't affected by that event. Right, so I'll just skip over this. This is just showing a lot of detail over here, trying to interpret these different the velocity profiles over here, combining with xenolith information. And of course, when you get to middle mantle and lower mantle depths, we don't have xenoliths. One has to use and tie it together with work that's been done in laboratories over here, putting these rocks under high pressures and temperatures to see what kind of mineral assemblage you would expect to have. Right, then one of the big mysteries and interesting things over here under Southern Africa, of course, is our South African super plume over here. And there, of course, there are two of these big seismic low velocity zones in the lower mantle. We've had some very interesting talks presented in the GeoTalk recently looking at this. Sue and Lou and Tom Torsvik and others have come up with theories locating these plumes, this plume over here, to the position of kimberlites at the time they were erupted. So, of course, you've got to dial back the position of your continents and showing that many of your kimberlites arrive from the edges of this feature. So that's important information that has been done subsequently. And so the question is, what are these features? Are they graveyards of subducted slab? Is this just due to a change in, you could say, temperature, so places where perhaps heat is escaping from the plume, or are they more long-lived features that are due to changes, I suppose, in mineralogy or chemistry? So that's the kind of question. But I suppose what you look at over here, one of the very important things to try to help you distinguish between those different hypotheses is the sharpness of your boundary. If it was just a thermal effect, you'd expect it perhaps to be more gradual. If it's actually due to different chemistry of your mantle, then it would be perhaps sharper. So this is part of what's been done to try to get as much resolution as we can. So you can see, looking at over here, different earthquakes were, I suppose, recorded at different epicentral distances. You can see the difference in distance is from 93 degrees to 110 degrees, a distance of 17 degrees, or about 1,800 kilometers. That's more or less the length of the array. And you're able to see that sort of vertical line over there shows quite a sudden delay, somewhere between epicentral distance of 100 degrees and perhaps 102 degrees. And that would seem to imply that it is in fact quite a sharp boundary, not just a diffuse boundary. So that's some other very important first order observations that have been made over here as to what the nature of that South Africa, of this super plume is down below here. Right, and that really just takes us to anisotropy over here. Anisotropy, of course, refers to where your rock has as you could say, a fabric that gives you different velocities in different directions. And the first thing over here was to look at the PN anisotropy. The nice thing about it is you know exactly at which depth in the crust that is arising. And Tarzan Quadiba over here looked at it and he showed that there's a strong anisotropy with your faster velocities directed more or less in almost a north-south direction. You see the rose diagram over there, and you can see where your velocities are faster, up to 8.4 kilometers per second along the one direction, and a lot slower down to perhaps 8.2 kilometers per second in the perpendicular, the orthogonal direction. Work was done using shear wave splitting by Paul Silver and his crew over here to determine not only the amount of shear wave splitting, the delay, but also the directions here. And you can see the strong fabric that was determined. Now, this is exactly the work that Dimitri's been doing. He's been expanding on this, looking at the work in East Africa using more recent data, and he's now looking at Southern Africa over here to come up with better resolved models over here to try to see, you know, what is the direction and magnitude of your shear wave splitting. But generally, what is argued over here is that these directions of anisotropy are aligned to tectonic fabrics, and so this is a fossil anisotropy, and it's not due to the current day plate motion. Right, then in around the Kimberley array, they were able to do with all those more stations over there, do a lot more detailed study over here. And they found that there's a kind of a domain boundary over here passing through the array, and on the north western side, you get perhaps stronger anisotropy, while on the southeastern side, a weaker anisotropy. And there have been many other studies over here trying to look at domains over here in the craton. On the right-hand side, you'll see a line they say in the Colesberg lineament, and this is something that's attracted a lot of interest, both from potential field studies over here as well as seismic studies, as what is the meaning of this lineament. Okay, and over here, this kind of pops it all together. Over here, we have different polarization directions, fast, slow, and over here, it's grouped together in our different tectonic domains over here to try to summarize it all together. And I mean, this would take quite a lot of thought to figure out, so I'm not going to go into detail over here. But again, this is really supporting that the previous slides over here showing that you get different strengths of anisotropy and directions of anisotropy in your different tectonic domains. So it's related to the domain, to the fossil fabric, rather than present-day plate motion. And so it was all assembled over here into a big broad brush assemblage of our continent over here, showing how these different tectonic fabrics would have been inherited. And I guess so Finito is busy writing up his recent studies, particularly using the recent data. And the question will be: does his findings now, does it support this general model, or does it show some variation? Maybe he can comment on that. Right, so this is really then, in conclusion over there, they compared, there was a meeting over there comparing what was found with all the seismic studies on the Karpov craton and the Slave craton and other cratons around the world, and seen, is there a global picture of anisotropy over here? And that's summarized in what we had over here, these different regions in North America, in Africa, and Australia. And I won't go through that in detail. These are just other studies, but these are the general models for these 4 regions in terms of where you find your anisotropy, how strong it is over here. And generally, the question that you will see over here, that there's no one model that fits everything over here. You get variations between your regions over there. Not one size fits all over here. Right, and that really takes me to the end of what has been done with all the SARSI data. That was the experiment that ran from 97 to 1999. And over there, of course, what had happened in 2007 when I gave this talk, it was clear over here that a great deal had been learned from this investigation. And I suppose at last count, maybe 50 or 60 papers have been published using this data. Of course, the data has been set free, so people continue, including ourselves and groups all around the world, to mine this data set, to test new ideas, and to see what they can learn about Earth structure and evolution. At that time here I suppose generally in 2007, there hadn't been that much integration with other geophysical data sets, specifically our potential fields and our magnetotellurics. And since then, we've done, some of that has been done, but I think there's still quite a lot of scope to, in all our studies to integrate our results better, particularly with things such as the SAMTEX experiment and 3D modeling that we're doing. And actually at that time, I suppose when I came and joined this, of course, all the equipment and the software and all that had been brought in as part of this program. And since then it had kind of dispersed. Of course, the stations that were on loan had been returned to Pascal, the software and equipment, they'd all been scattered. And so there's little left at our African universities. And what we've really been doing over the last 10 or 15 years is trying to rebuild that capacity, getting some of our own broadband seismographs, both here at the Council for Geoscience, and trying to rebuild that group. And you are all part of that effort. And so that really takes me to the end of that presentation. And Steph, I've gone on for quite a long time here, so maybe this would be a good time to stop today. I've got other presentations which go into more detail on the Bushveld complex, really presenting Eldridge Kagaswani's work, where he took the same data but focused in on the Bushveld complex and tried to extract as much information as he could. I'm firstly looking at whether or not there's evidence for a continuous high velocity layer, and then even zooming in further and trying to come up with a structural interpretation. And then also some very interesting work he did as part of his thesis. These are the, I suppose, the 3 papers that came out of his thesis, looking at the rheology of the crust and upper mantle. And that's combining heat flow with a seismic velocity. And then, of course, we've got other work that's been done using ambient noise tomography and also joint inversion of gravity and surface waves, the work that Ranto did in the Congo Basin, which would be, I suppose you could say, very similar to what Herman will be attempting here in Southern Africa. So I've got quite a lot more that I could show, but maybe this is enough for today. What do you think?
Thank you, Ray.